Hi everyone, welcome back. Here we are with example 7 from topics 6.7 and 6.8. We're going to revisit our good friend, the Fundamental Theorem of Calculus, but this time we're going to use that theorem in a way that's a bit different. We're not going to find area under a curve, although that's still what's going on. We're going to actually use our integration formulas that we've been compiling throughout this particular group of lessons and evaluate a definite integral that way. So let's go back to the FTC. So if you recall the Fundamental Theorem of Calculus in this blue box, which was introduced all the way back in topic 6.4, it's a very important theorem. It says the integration of f of x with respect to x as x goes from lower bound A to upper bound B is just the antiderivative capital F evaluated at B subtract the F evaluated at A. And like I said, we want to make sure that we recognize that relationship, that capital F is the antiderivative of F. Now, this takes on a bit of a different look because we know how to find these antiderivatives. We know these procedures, these rules and formulas to get the job done. So these problems, like I said, they take on a completely different look now. And man, are you going to see a lot of definite integrals in your day for the rest of your calculus career. So example 7 has 6 different versions of these problems that integrate some of our, no pun intended, they integrate some of our formulas that we've learned into this idea. So let's go ahead and take a look. First of all, in part A, antiderivative of 10 with respect to x from -2 to 4, or the integration of 10 from -2 to 4. Well, hopefully you remember that when you integrate a constant, you just get that constant times the variable x that matches our independent variable denoted by that dx. Now, instead of putting a plus c here, and nope, you don't worry about plus c's anymore, we'll explain why in a moment, I want you to evaluate this at 4 and -2 and then subtract those. One of the most popular ways to show that from a notation standpoint is the vertical such that bar, where you can attach those two boundaries in that same order to that bar. What this tells the reader in math is that you're going to plug in both of those, and it's kind of a contextual understanding by all that we would subtract those because we know that this is part of the fundamental theorem of calculus notation. So you will plug in 4 for x, so 10 times 4 is 40. You would subtract, and then you'll plug in -2 for x, which of course is -20, and then you just clean up your arithmetic, and boom, there is your answer, 60. The area under the graph, y equal 10, between -2 and 4 would be 60. Now, if you remember the other day, we talked about another short way to do these, and that was just to simply take the difference between the boundaries, which is 6, and multiply it by the constant. That will work as well if you wanted to do that a little faster. But it only works when you have a constant there. Now let's take a look at some that are a little bit more challenging. Integrate x squared plus the square root of x with respect to x from 0 to 1. Well, one thing is for certain, this radical x you might want to think of as being x to the 1/2 power so that you can better integrate him by using our formulas. So x squared would become x to the 3rd over 3 when you take his antiderivative. And the x to the 1/2 would become x to the 3/2 over 3/2, which I know we talked about how that's just going to be a 2/3 here in just a moment. We'll change it in our next step, and then you're evaluating from 0 to 1. Now, I would certainly clean this up a little bit, make your life a little bit easier. So we'll move that 2/3 to the front. And then as far as x to the 3/2 is concerned, you could call this the square root of x cubed. You might find that a little bit easier to deal with if you prefer to not use the fractional exponent. But regardless, I don't think it's going to be terrible in this problem because of the boundaries being probably the two easiest numbers that we could have ever come across. So if you plug 1 in for x, 1 cubed over 3 is 1 over 3. Plus, and then if you take 1 and plug it into this x, well, the cube of 1 is 1, and the square root of that is still 1. And so it really doesn't change what you have. You got 1/3 plus 2/3. Now you'll subtract, and you'll do the same thing, but plug in 0 for x. Well, when you plug in 0 for x, basically, you got nothing, right? Nothing hangs around when you let those x's be 0. And so you can simplify 1/3 and 2/3 to get 1, and that would be your final answer. All right, these actually can go pretty quickly once you get into a nice rhythm. Let's take a look at part C, the integration of 2 times the secant squared. Well, one thing is for sure about this problem is it's kind of hearkening back to a couple of videos ago when we were talking about the integration of our trig words. First of all, that 2 is a constant, so you can bring him straight down in front. And then you have to think about what is the antiderivative of secant squared. Well, the answer to that is tangent, because the derivative of tangent is secant squared. Let's go ahead and stick with our angle that we have, or our variable, which is theta. And we'll use pi over 2 as an upper boundary and negative pi over 2 as a lower boundary, which makes a lot of sense. It's nice that we had these pi values as boundaries because they're a lot easier to work with in a trig expression. As far as the 2 is concerned, I typically will bring a constant out in front before I evaluate. You are more than welcome to keep the 2 inside to both. I'm going to take pi over 2, plug it in for theta, subtract, and then I'm going to take negative pi over 2 and plug that in for theta. And now we just have to know our trig ratios. What is the tangent of pi over 2? The tangent of basically what would be and I just noticed something. I'm terribly sorry about this. This doesn't have actual answers because the tangent of pi over 2 is 90. I should have seen that coming. The problem that we should be working on should have boundaries of pi over 4. So if you are an Avon student and you're working off your handout, it depends on which version. If you had an older version or if you're working with a newer updated version, you should have pi over 4s as those boundaries. Okay, I now have pi over 4s. If you're outside of Avon, you just kind of saw me make a kind of a fool of myself here, and I wanted to make sure that we take care of these. I knew that something was up because we weren't going to get answers. Because yes, the tangent of pi over 2 is a vertical asymptote, and I want this to have an answer. Okay, I looked over at my key and I thought something's not right. So here's our brand new problem. Right, hopefully everybody's caught up. So now what is the tangent of 45 degrees, the tangent of pi over 4? And the answer to that would be 1. Right? The tangent of pi over 4 is 1. Subtract. Now the tangent of negative pi over 4. Well, lots of different ways you can think about that. The unit circle is a great way, where pi over 4, of course, is located down yonder in quadrant 4. And since all students take calculus, we know that in quadrant 4, only the cosine is positive, which means the tangent is negative. So you're going to still apply that 1. It's just that he's going to have a negative value when you're in that quadrant. And so once you take your 1 minus negative 1 and get 2, you'll multiply that by the 2 in front. And this answer is now actually 4. All right. Let's take a look at part D. I promise the boundaries are correct in part D. We had a discussion in one of the previous videos about whenever you're integrating things that are a little bit more complicated, like 1 minus the square root of t over the square root of t with respect to t. And I highly, highly recommend that we change these square roots into fractional exponents. So we could write it something like this to begin with. And then we divide this into two completely separate fractions. Because you have a monomial denominator, that is allowed. Now, if you did not have one term in the bottom, that's something that you could not do, and the problems actually become a little bit more challenging, and we'll get to those much later. Now, at this point, we can go ahead and take our antiderivatives, we can take our simplification into play. 1 over t to the half is t to the negative half, and then, of course, t to the half over t to the half is 1. So that is going to be a much easier version of this original problem to take an integral. And just as a vocabulary term, the expression after the integral is referred to as the integrand. And you're going to hear me use that term from time to time. We have an equivalent integrand as our original problem, but one that's much easier to integrate. Integrate t to the negative half, you get t to the positive half over a half, which is the same as multiplying by 2. And then subtract, the integration of 1 is just t. Let me see if I can move these over a little bit. All right. And then I can apply my such that with my boundaries of integration. And I do like to emphasize the fact that it's nice to put this expression in parentheses when there's more than one term to denote that both terms will receive the 9 and the 4. So at this point, we're going to take 2 times 9 to the half, or also known as 2 times the square root of 9, might be an easier way to think of it, minus 9. And then we'll subtract the quantity. Now we plug in our 4. We get 2 times the square root of 4 minus 4. And when all is said and done, 2 times 3 is 6. 6 minus 9, I'm going to go ahead and write that down as negative 3, minus, and then 2 times 2 is 4, minus 4 is actually 0. And so we get a final result of negative 3. All right. Now notice there are a lot of things that can go wrong with arithmetic at the end of these problems, so you want to make sure that you're exercising just as much caution as you're working through the final stages of the problem, which really involve arithmetic, as you would the beginning of the problem, which involves calculus. All right, last couple of here. Integrate e to the x with respect to x from 0 up to this very strange boundary of natural log of 5. Well, one thing is for sure, this is probably the easiest integral formula that you have on this page, because the integral of e to the x is e to the x. Now we'll put our such that, and we'll use our ln of 5 and 0 as our boundaries. And when we plug them in, I think we're going to start to understand why natural log of 5 was a boundary. It's going to make the problem pretty easy to deal with. We need to recall from a previous course that e to the natural log of 5 in that environment basically cancel each other out. They're inverse operations on one another, and the answer that you get would be 5. And then e to the 0 is going to be a 1, and therefore our answer is 4. And then finally, part F. The integration of 3 over x with respect to x as x goes from 1 to e squared, another unusual boundary. But there must be a reason for it. If we drop the 3 in front, all we have left is 1 over x, and the integration of 1 over x, if we recall, is the natural log of absolute value of x. That was hit in our last video. Now notice in all of these problems, you don't have a plus c. We draw our such that bar and our boundaries e squared and 1. And I said I was going to talk about why there isn't a plus c. Well, if you think about in any of the problems that we've done thus far, if we had a plus c after our expressions, by the time we plug in the boundaries and subtract, those two c's would be connected by a subtraction symbol and would thus disappear. And so we don't even worry about plus c. I know it's very contradictory. You're going to have to remember plus c if you don't have boundaries on your integral, but then you can forget it completely when you do have boundaries. Finishing up this problem, we are now going to plug in our e squared and 1. I'm going to factor the 3 out. As I plug in e squared for x, I'm going to live life on the wild side and not put absolute values around e squared. And the reason is because I'm very confident that e squared is already positive. And then I can subtract the natural log, and I'm, again, equally confident that 1 is positive, so the absolute values aren't really needed. In our next step, 3 comes in front once more, and then we have natural log of e squared, which means the 2 can come out in front, and then the natural log of e is 1, so you just simply have a 2. And then for the natural log of 1, that's going to be equivalent to 0, and then 3 times 2 is 6. A lot of things going on, especially in these last two problems. These last two problems really push students to really have a command over the exponentials and logarithms. There are a ton of videos out on the market that you can watch on YouTube that will really help you. Just Google exponential functions, logarithmic functions, properties of exponential functions, properties of logarithmic functions. That will help you bring yourself up to speed. You can also check out those kinds of videos on Khan Academy. So this takes care of our example 7, that uses this idea of the fundamental theorem of calculus, where you're actually doing the integration by using the formulas that we've talked about. Thanks for joining. We'll see you next time.